So what is differential privacy, and how is the PrivateSQL that you've developed going to enable our audience here to make differential privacy SQL queries more easily?
All these technologies, the goal is to protect the computation process from leaking sensitive information. But another important aspect is, so for example, in this case, when somebody does a computation, the computation is based on the original sensitive input. So then we also need to ensure that the computation output doesn't leak sensitive information about the original input. This decentralized intelligence, we hope, can help make much better decisions overall, make more fair decisions.
All right, welcome to Super Data Science live on stage at the Open Data Science Conference West, ODSC West in San Francisco. Let's get a crowd cheer. Nice. I'm your host, John Krohn, and I'm joined today by a very distinguished guest. We have Professor Dawn Song. She leads trailblazing research at the intersection of deep learning and decentralized systems like the blockchain. She's been a professor in computer science in the computer science division of UC Berkeley for 15 years, which, as many of you know, is a #1 university in the US overall, and also #1 for the computer science grad program and for the blockchain. So it seems like you're in the right place for that. Maybe you're even responsible for that. At Berkeley, Professor Song co-directs a new campus-wide blockchain and Web3 center called the Center for Decentralized Intelligence. And she's part of the illustrious Berkeley AI Research Lab, BEAR. She's authored over 300 papers, leading to over 80,000 citations. She's won countless awards, including the Genius Grant, the MacArthur Fellowship, and she's separately the founder of Oasis Labs, a data privacy startup that's raised over $45 million in capital. So let's start, Dawn, with the new Center for Decentralized Intelligence that you co-direct. Tell us more about the center and why it's called the Center for Decentralized Intelligence. Maybe tell us what decentralized intelligence is.
Great. First, thanks a lot for having me here. So let me first talk a little bit about the new Berkeley campus-wide blockchain Web3 center called the Berkeley Center on Responsible Decentralized Intelligence. So the center really, the goal or the mission statement is to advance the science and technology of Web3 decentralization and decentralized intelligence, and to make it universally accessible and to help promote a responsible digital economy. And the center is called Responsible Decentralized Intelligence because the center actually focuses exactly on 3 key aspects. Responsible decentralized intelligence. Okay, let me talk a little bit more, go into a little bit more detail for this. So first, responsible. As we all know, the technology field is moving really fast, and we are developing really exciting new technologies all the time. I know people, have been talking about the large foundation models, stable diffusion, and so on. Mm-hmm. And also in the Web3 world, we are developing really exciting new technologies as well, including blockchain, and people have heard a lot about NFTs, metaverse, and so on. Right? And Meta even changed their name, right, from Facebook to Meta. But however, we all know that these technologies, it's just like what people say, right? With the great power, you also have great responsibilities.
Right.
The technology can be misused, and we have seen already in the real world, these new technologies are being misused, both in terms of, for example, people are now continue to worry about, fake videos, fake news, and so on. And then in Web3 world, of course, there's a lot of scams, there's a lot of attacks, and so on. So one key, especially as we move forward in this technology-driven, advancement, is that we need to really make sure that the technology is being used in a responsible manner. And when I say responsible, there are many different aspects of being responsible, including we want it to be privacy preserving, we want it to be regulatory compliant, and it needs to be fair, has good ethics, and also we want to enable leveling playing field to enable innovation, and supports diversity, inclusiveness. So there's a long list of the different aspects of being responsible. And for the center, the number one goal for the center is to ensure that as we develop these new technologies, we need to develop new approaches and find new solutions to ensure that technologies are used in a responsible manner. Right. So that's why the center starts with responsible being the first word. And the second one is decentralized. Mm-hmm. So in particular, the center focuses on, as I mentioned, decentralization technologies. The center aims to develop various new advancements in decentralization technologies, and this is broadly ranging, including blockchain, Web3, decentralized data science, decentralized intelligence. Because the goal or the key of decentralization is that we can build systems without relying on central trust. We can build systems that actually can support, that actually can work in this decentralized manner, essentially built on decentralized trust, or sometimes also people call it trustless. And given that I also have done research in computer security for a really long time, yes. over 2 decades.
Yes.
And we all know, right, essentially I think building systems that doesn't rely on centralized trust actually is the most secure way of building secure systems. And hence, I do strongly believe that in the future, we are going to see more and more of these decentralization technologies, decentralized systems, because they are more robust. You can build it in a more secure way.
Right, so decentralized systems allow us to have more trust in the system, and in a way that doesn't rely on kind of a central administrator.
That's a really good point, yes. It allows you to have more assurance that the system will work, even when there are various either attacks or certain central parties or certain parties are compromised and so on, because it relies on decentralized trust so that you can, in the end, have more assurance that of the properties that you want to ensure or enforce for the system.
Nice. And so you mentioned that you think this is going to develop, that we're going to have more of this in the coming years. What's that going to look like maybe over the next 5 years and then over the coming decades? How do you see decentralized intelligence evolving? Right,
that's a really good question. And also, yes, so the third key aspect is intelligence.
Right.
And for intelligence also, it's really broad ranging. I mean, here we are at a data science conference. It's intelligence, of course, part of it is coming from data, and ultimately it's about making decisions, how we can, as individuals and as groups and as society, how we can make the best decisions. And also we want to, in the future, we are going to see more autonomous agents
sure.
and with AI, machine learning, and so on. So the third key aspect of the center is how we can enable these autonomous agents and in a decentralized manner as
right.
well. So for example, going into the future, we are going to have more, for example, like self-driving car technologies and other. Already we have a lot of smart agents deployed at home and other places, and they are going to continue to be smarter and smarter, and they are going to make more and more automated decisions on behalf of their users and companies and so on. So this is all in the broad realm of intelligence, and
right.
and I do strongly believe that in the future we are going into a decentralized intelligence future, where it's not like all this intelligence is controlled by centralized entities or the top tech companies and
right.
so on. Instead, I do strongly believe that first we need to have decentralized intelligence. We need to have these different autonomous agents or even personalized assistants, virtual assistants, and so on, that are more controlled by individual users to essentially work on the best of their interests, work
right.
on the behalf of individuals. And also, ultimately, this decentralized intelligence, we hope, can help make much better decisions overall, make more fair decisions, that actually can take into account different entities and different users' interests, and provide more privacy-preserving solutions as well.
Nice. So our audience here, many of them are probably expert with the intelligence part of responsible decentralized intelligence, and probably have lots of ways that they are thinking of creating more automation in our world. So what can our audience be doing? What can data scientists be doing to be thinking about having decentralization in their applications?
Oh, that's a really good question. So yes, actually, as part of the research projects that we have been doing in the Berkeley RDI Center, is that we're actually developing a new platform called Decentralized Data Science Platform.
Perfect.
So I can, yes, that actually, the goal is to help data scientists and practitioners in data science and machine learning in the real world to actually make it easier for them to develop decentralized data science applications with strong security and privacy guarantees. So I can tell a little bit of the story,
dig into it.
How this came about. So this actually started from a recent partnership that Oasis Labs did with Meta.
Yeah.
So in this partnership, Oasis Labs worked together with Meta, developed new cutting-edge technologies in privacy preserving AI machine learning area. So essentially, in this partnership, we developed the cutting-edge privacy technologies to help enable AI model fairness assessment. So for example, with Instagram and other applications and Meta, users get recommendations served from AI machine learning models. Then, of course, there's huge questions about whether these machine learning models are actually fair, whether they have certain biases and so on. And many of you may have seen a lot of discussions about how important it is to ensure that these machine learning models are fair. So then it's a really important question for Meta to figure out how to measure this fairness for their AI models. However, in order to do that, it requires them essentially, for this assessment, for this AI model fairness assessment, it requires essentially knowing the essentially certain sensitive attributes of users. For example, if you want to measure fairness across genders, then you need to know for a certain user whether the gender of the user and other, for race and so on.
And we don't necessarily want those attributes to be sent to Meta.
Exactly. Right, because in that case, then Meta will be knowing too much about the user, then there's privacy concerns.
This episode is brought to you by Iterative, the open source company behind DVC, one of the most popular data and experiment versioning solutions out there. Iterative is on a mission to offer machine learning teams the best developer experience with solutions across model registry, experimentation, CI/CD training automation, and the first unstructured data catalog and query language built for machine learning. Find out more at www.iterative.ai. That's www.iterative.ai.
So then in this case, so what Meta did in collaboration with Oasis Labs and a few others is, so first, Instagram users can opt into a survey run by an independent survey operator. And then in that case, if the user opts into the survey, the user can fill in a form providing information about their gender, race, and other types of sensitive attributes. Mm-hmm. And again, as we just discussed, it's of critical importance that this information is not shared directly with Meta. However, this information is crucial to compute this AI model fairness assessment. So then what we developed is actually a combination of cutting-edge privacy technologies, including secure multi-party computation and homomorphic encryption, and also we use some zero-knowledge proof to ensure that the actual computation process actually is proper. For example, the data is within a certain valid range and so on. And also differential privacy. So essentially these, what I just mentioned, these are actually the key components of modern secure computing, privacy computing technologies. Yeah. They are different technologies, but they all serve essentially the similar goals of ensuring privacy protection for computation.
Yeah, maybe we could dig into some of those a little bit more. What is homomorphic encryption?
Okay, that's a very good question. So homomorphic encryption is a type of encryption with a special type of properties. It's actually really beautiful and very elegant. So basically, the idea is normally with a normal encryption algorithm, you take a plaintext X, you generate an encryption, a ciphertext of E of X. E here just stands for encryption function, E of X. And for normal encryption, then you get take a plaintext X, you get E of X, and you take plaintext Y, you get E of Y. But for normal encryption, E of X and E of Y, in this case, they don't really have any particular relations and so on. So, but with homomorphic encryption, what happens is that it enables a certain relationship between a certain mapping between the plaintext and the ciphertext, in the sense that, for example, if I give you plaintext X and the ciphertext E of X and plaintext of Y and E of Y, then in this case, we say it's additively homomorphic if then now I can compute X plus Y, the encryption of X plus Y, which is E of X plus Y, from E of X and E of Y. In this case, you can say it's addition of E of X and E of Y in the ciphertext domain.
Okay.
So that's additive homomorphic encryption, and similarly, you can do multiplicative homomorphic encryption as well if the multiplication relationship holds as well. And then if the encryption algorithm satisfies both or enables both, then we call it fully homomorphic encryption.
And then so what does that enable for us? What does that kind of encryption enable us relative to maybe other kinds of encryption?
That's a great question. So with this capability, what you can see then is quite amazing. So basically, if I'm a user, I'm holding a plaintext X, and then I can generate the encrypted version, the ciphertext E of X, and if you are the serial, the program, and then basically from my encrypted data, then you can do all sorts of computation.
I see.
So then essentially you can compute on private data without seeing it.
Got it.
So you can enable computation over encrypted data.
So in the meta, to keep going with the meta example, you can have private information that users have about sociodemographic characteristics, and that can stay private to them by using homomorphic encryption. That so then just the homomorphically encrypted information gets sent to, say, Meta, and they can perform some computation on it and then give some API response back without ever having actually seen the private data.
Yes, exactly. So in fact, actually there has been research done in the space where you can use this type of technology. So for example, if you want to evaluate over a machine learning model, but without letting the model to actually see the plaintext of the input, you can send an encrypted version of the input, and then by using homomorphic encryption, you can then basically evaluate the model, compute the inference on this encrypted data, and then in the end send the encrypted inference results to the end user, and the end user can decrypt it and learn the actual inference result.
Nice.
So however, there is a catch to this. So that's why in our work with Meta, we have to combine all these different technologies. Is because fully homomorphic encryption today, it's a great technology. It's really beautiful, but it's still very expensive, especially when you want to compute over a really large amount of data.
I see.
And for example, the example that I just gave, if you want to evaluate over over encrypted data for this machine learning model, even just a small model, it can take you actually a very long time to do this. So then in the end model fairness assessment work, our goal is to actually be able to do this computation over like millions of users. And so we need a more practical solution, a more efficient solution. So that's why in this case, we also combine secure multi-party computation. So with secure multi-party computation, in this case, you have multi-party computation.
Multi-party computation.
Right. So with fully homomorphic encryption, you are the server, and there's only one entity who can do this computation over encrypted data. But however, with secure multi-party computation, you do secret sharing across multiple parties, so that each party actually doesn't know the actual secrets.
Right.
But then altogether, in collaboration, they can actually compute the
Right.
results, and then it's also a form of computation over encrypted data. But in this case, the trust model is different. So in the fully homomorphic encryption case, the trust model is that we don't need to actually trust anyone, because as a server, you don't actually see any data, you only see ciphertext.
Right.
But in the multi-party, secure multi-party computation setting, we need to make the assumption, the trust assumption, that the attacker can only compromise at most a certain threshold
I see.
of the parties in the group.
I see. So an attacker could we can assume that attacker could only compromise certain parties in this multi-party system. And so even if an attacker got access, they wouldn't be able to combine the information together.
If they only have access to at most a certain threshold, a number of servers. And but the advantage of this approach is that the computation is cheaper than in certain cases, than in certain settings, than fully homomorphic encryption. So that's why in our work with Meta, we actually combined these different technologies to ensure that we have the most efficient solution and at the same time have the better privacy protection as well.
Nice. Another term that you mentioned earlier when talking about this project with Meta was the idea of differential privacy. Mm-hmm. So what is differential privacy, and how is the PrivateSQL that you've developed going to enable our audience here to make differential privacy SQL queries more easily?
Okay, great. That's a great question. So when we talk about privacy computing, actually there are several different aspects of privacy that we need to pay attention to. So the first, when I talk about fully homomorphic encryption and also secure multi-party computation, and also there's another type of approach using secure hardware, secure enclaves. So all these technologies, the goal is to protect the computation process from leaking sensitive information. So basically, the goal is to compute over encrypted data, but using different types of technologies. But another important aspect is, so for example, in this case, when somebody does a computation, the computation is based on the original sensitive input. So then we also need to ensure that the computation output doesn't leak sensitive information about the original input. So for example, some of our earlier work actually in this space also relates to these large language models. So we showed that with these large language models, and also it's not just unique to large language models. So I'm just using that as an example.
Sure.
So in general, these models, they have huge, deep learning models, they have huge capacity. So there's another question whether they actually remember training data. Mm. And if they do, whether attackers can actually extract the sensitive information from the original training data by just querying this model without even knowing the architecture or the parameters, these details of the model.
So GPT-3 could theoretically, if trained on private data, it could be memorizing those data, and then you could potentially write queries that would allow you to extract private information from a large language model like that.
Yes, absolutely. That's actually exactly what we did. So we did, right. Okay. So we did a number of experiments. So one interesting experiment we did, it was a smaller language model where we trained the language model over a data set called the Enron data set, which naturally contained
the Enron dataset.
Yes, the Enron email dataset. So we don't have time to go into that, but it relates to the Enron, the company, earlier. Yes, there was a case. So that's how that data was made available.
Right.
And the Enron email dataset naturally contained users' social security numbers and credit card numbers. So our work shows that by when you train a language model over this data set, an attacker, by devising some new attacks, can, from just querying the language model without knowing the details of the language model, can automatically extract the social security numbers and credit card numbers that were in the original training data set.
Wow.
So this is an example illustrating that as we train these large models, it's really important to pay attention to users' data privacy as well. And later on, we extended the work on larger language models as well, including GPT-2, and we are actually looking at some newer models, including the models in the category of stable diffusion and so on. So all these illustrating that as we compute over user-sensitive data from the output, in this case, either it's the inference from a machine learning model, or it can be other analytics and so on. So for example, if we are computing analytics over users' data, then it's important that the computation output doesn't leak users' sensitive input. So then what's the solution to this? So today, actually, the gold standard is to make your algorithms differentially private. So differential privacy is a formal notion of privacy. At high level, what it says is the reason it's called differential privacy is, so for example, I have a data set, and then I have a neighboring data set with your data added to it, with your data point added to it.
Yeah.
And now I want to compute algorithm, either training a machine learning model or compute data analytics query over this data set, actually over these two neighboring data sets. And then my algorithm is randomized. So the results of this randomized algorithm over the data set will produce a probability distribution. So we say that my algorithm is differentially private if the probability distribution generated from an algorithm over these two neighboring data sets with or without your data points is indistinguishable to the attacker.
Right. So if there's a difference between the data sets, I guess that's where differential comes from.
Exactly.
But we can't tell a difference in these probability distributions that are computed from it.
So if that is the case, that means then your data is pretty safe. In the sense that as an attacker, from just looking at the computation output, the attacker cannot tell whether your data is has been used in the computation or not. And so intuitively speaking, provides protection for your data.
I see.
What do you think about the Super Data Science podcast? Every episode, I strive to create the best possible experience for you, and I'd love to hear how I'm doing at that. For a limited time, we have a survey up at superdatascience.com/survey, where you can provide me with your invaluable feedback on what you enjoy most about the show, and critically, about what we could be doing differently, what I could be improving for you. The survey will only take a few minutes of your time, but it could have a big impact on how I shape the show for you for years to come. So now's your chance. The survey is available at superdatascience.com/survey. That's superdatascience.com/survey.
So that's differential privacy.
Yes.
And in our work with Meta, so we also use differential privacy to protect the computation output from leaking sensitive information about users' input. And a couple of things I can add.
Well, yeah, so I'd love to hear about the PrivateSQL that's related to this.
Right,
so,
exactly.
Yeah.
So actually from this experience, a couple of lessons that we have learned that I actually like to some of the follow-on work that I can share is, so overall, all these technologies, they are great, and there have been lots and lots of papers, maybe hundreds of papers or even more written on the topic. But most of the papers actually, mostly the great ideas have mainly been just sitting on the bookshelf. In the real world, in practice, we have seen very, very little real-world deployment of these great ideas, these great technologies. So for example, differential privacy, I think right now has been, so Google has done some special use case, and Apple has done some special use case using differential privacy. And these are the leaders in the space, in industry. And even in their case, it's still very specialized use cases. So overall, I think more and more people are hearing and learning about differential privacy, for example, but most people have never really, seen how it's deployed in the real world, know actually how to use it. So this started as research work in my research group at Berkeley, and then now Oasis Labs has been actually productizing it, making it actually as a commercial product, is to really solve this problem is to make this differential privacy technology, in particular in this case, enabling differentially private SQL, to make it really easy to deploy, and hence more data scientists, more practitioners can benefit from this technology. So this also was motivated actually earlier from our collaboration with Uber. Actually,
with Uber, the rideshare company.
Yes, a few years back. So basically, for Uber, for example, and also lots of companies have this the same issue, is that they have a lot of sensitive users' data. And then this data, of course, can be very useful to provide business insights to help them improve their service for users, and also figure out how to best deploy their resources to improve their overall business. And so ideally, they want to have a lot of their either marketing departments or business departments and so on. So just in general, for their business operation, they want to have different analysts or even just people in these departments to be able to somehow use the data to gain business insights. But of course, given that this data is really sensitive, for example, Uber has every user's rides data, from like your start and location and time and so on. It's really sensitive information.
Yeah.
So then they can't give access to these marketing departments and these other departments and so on. And in fact, actually, Uber in the past had fired employees.
Yeah, Uber is not famous for for being very good about privacy.
So in the past, they had fired employees who actually misused their access rights to look up certain
God
users.
mode.
Right. Okay. So then essentially they're in a dilemma. So either they just lock down the access. So then they can't use the data. Their employees cannot use the data to improve the business and improve also user experience overall. Mm-hmm. Or if they give access, then they have this huge risk of privacy and data breach and so on.
Right.
So then in this case, actually PrivateSQL is actually a great solution for them. Because with PrivateSQL, so also let me tell you a little bit in terms of the technology for PrivateSQL.
And so PrivateSQL, anyone here can use, right?
Exactly. So that's a technology that Oasis Labs now is commercializing.
Oh, you're commercializing.
Right. Okay. So what it is again, for differential privacy, as I mentioned, it's a formal notion of privacy, and you actually have to, for each algorithm, you have to develop differentially private version of the algorithm. So for example, if you want to compute a count, if you want to compute a sum or average and so on, you need to develop like a differentially private version of these analytics. And depending on the actual data set attributes, there are different differential privacy mechanisms that you can actually use. That's best for your privacy and utility trade-off. So in any case, usually it requires a lot of expertise in differential privacy to actually use it. But of course, most data analysts, they don't really know about differential privacy.
Right.
And also, it's difficult you also don't want to change the backend database to embed differential privacy mechanisms in the database, because then it's difficult to actually deploy. You have to change the backend infrastructure. So what we have done with this PrivateSQL is basically you can view it as a layer in between the data analysts and the backend database. So basically it sits right in front of the backend database. So when users submit queries, this SQL data analytics queries, they will get automatically rewritten by our PrivateSQL this thin layer. And it will automatically write the SQL query into a new SQL query with differential privacy and other privacy mechanisms embedded into it. And then this new SQL query, we call it essentially intrinsically private query, then gets executed on the backend database. And then the database will return some results, and our thin layer will also do some post-processing in certain cases, and then in the end return the result. So the final result in this case will be guaranteed to be differentially private. And also, it can guarantee other privacy properties that your privacy policy dictates as well. So then in this way, as you can see, we've changed this deployment problem, making it really, really easy. So in this case, we don't change the workflow at all. So the data analyst doesn't need to know anything about differential privacy, and we don't change the backend database as well.
Perfect.
All you do is just put this thing there in front of the database, so it's really, really easy to deploy. And now, so in Uber's use case, now they can allow their analysts to use the data without worrying about data leakage, privacy violation, and so on.
Great.
So that's just one example of the real world use case. And we have the pilots now also with the BMW and also in healthcare with hospitals and so on. So we do hope to actually bring this product to Google GCP and Amazon AWS very soon. So we hope that more companies and more data analysts, data scientists actually can benefit from
It sounds super useful, and those were crystal clear use cases. And I bet lots of our listeners and our audience members here can't wait to be able to embed that kind of technology in their organization so that they can have potentially sensitive information still be used for business functions in a way that's safe and secure. That sounds great. So I want to turn questions over to the audience in a moment, but just before we get to that, I want to bring up a topic that I think might particularly interest this data science audience. So you've authored many papers on deep learning, and you've talked about it at length in talks that you've given and in interviews that you've given. So what is the relationship between deep learning and the kinds of topics that you've already talked about today? So responsible decentralized intelligence. And in particular, I think there's a term federated learning that it'd be great to introduce us to.
Okay, great. Yes, so federated learning is actually another component technology that in privacy computing, that's in particular for machine learning setting. And that's actually, in a second, I'll talk about this responsible data economy as well. So federated learning, the goal of federated learning is, again, you want to train machine learning models, but of course, a lot of the input is sensitive. So you want to have a good way to protect users' data, but still be able to train these machine learning models. So the idea of federated learning is, unlike normal machine learning training, for example, where users' data is collected and all sent to the central server to then train the machine learning models. Now, of course, in this case, as you can see, the central server now essentially sees everyone's data, and you really have to trust the central server not to leak your sensitive data.
So it's kind of similar. So where PrivateSQL allowed a data analyst to run queries and get summary information in a way that keeps database information private, federated learning analogously allows a machine learning algorithm to train without needing to bring in private information centrally.
Exactly. That's why it's called federated learning. Of course, it can also be extended. We also call it decentralized machine learning in certain cases. So in federated learning, the user's data stays on each user's device. They are now sent to the central server. So instead, these distributed devices, they would essentially work together in coordination by the central server in this case, where only, you can call it the model updates, for example, the gradient updates, is being sent to the central server, which aggregates these gradient updates to train the machine learning model in iteration. And it's called federated learning because now you have this federation of different devices where users' data is only stays on users' device, and users' data only stays on users' device. It's not sent directly to the central server. And further extending to this actually decentralized machine learning, in this case, you don't even have the central server. You can do this purely in a peer-to-peer setting, or actually using some other decentralized network to do this. So speaking of this, so the other thing I wanted to share also is that so federated learning, and also actually together with researchers from Google and a number of many other researchers, we have essentially a survey paper on federated learning. both a survey and also talks about, I should call the overview paper on federated learning. That's actually, I think, the most cited paper in federated learning today.
Oh, really? The most cited paper in federated learning?
In federated learning.
Yeah.
I think, right. It has many thousands of citations. And that's a good reference for anyone who is interested in learning about it. It really talks about the different types of federated learning, the different applications and open challenges, and so on. But with that, maybe I can briefly talk about, so I talked about these different technologies.
Yep.
Homomorphic encryption, secure multi-party computation, and differential privacy, and federated learning. And all these, I call them component technologies for responsible data use. So the goal is really, as we all know, data is a key driver of modern economy, and also it's really the lifeblood of AI machine learning. Without data, you are not going to be able to learn anything. But of course, a lot of this data is really sensitive, and going forward, the problem is only going to get worse and worse. So it's really important that as we do data analysis and machine learning, we enable this responsible data use, including providing better privacy, and also ensuring that users actually get fair value or get benefits from their data, and so on.
Nice.
So overall, this is what I call leading to a responsible data economy.
Yeah.
And there are, in my mind, so there are three key principles of a responsible data economy. One, as I mentioned already, is providing better privacy, and also, more importantly, providing this data rights, so that users can actually take better control of their data, and in this case also will help. So that's one. So this can serve as a foundation for ensuring that data is not being misused, and also secondly, ensuring that data actually users get fair value, get sufficient benefits from their data. And the third one is how we can, combine the society together to ensure that we do get max use,
max value
out of the data.
Nice.
For the best interests and social welfare, for the whole society.
Yeah, so no question we have a data economy today, and in the future, the data will drive more and more of the economy. It's great to be thinking about these responsible aspects of it. So what can our listeners or our audience members here do in order to be developing a responsible data economy going forward? I've heard about your CoLink initiative. So it sounds like that might particularly be of interest to the data scientists here, as a decentralized platform that makes it easy to develop and deploy privacy-preserving data science and machine learning technologies and applications. Could you tell us a bit more about that?
Great, thanks. Yeah, that's a great question. So, so this also actually stems from our experience working with Meta. So as I mentioned, we developed this privacy-preserving technologies for AI model fairness assessment. And so the project has been very successful. It's rolled out to the real world.
It's public now, right?
Yes, it's public
CoLink,
now.
C-O-L-I-N-K.
Okay, so first, right, so yes, but before that, so the project with Meta that I mentioned earlier also is rolled out in the real world, and it's really the first of its kind, large-scale deployments of privacy technologies for AI model fairness assessment. However, from that project, what we learned is actually the time it took us to develop the algorithm is actually relatively a small fraction of the overall system, because we need to deploy the system in the real world, and this real world deployments, building the actual, in this case, distributed decentralized system, we actually have multiple nodes running to do the secure multi-party computation with different entities. In this case, actually several universities participate in this as well. The whole system development and deployment actually took the bulk of the time for the project. So then this got us thinking, similar to the project of PrivateSQL, we wanted to make it really easy for analysts and developers to actually use differential privacy. But then in this case, we want to make it really easy for developers to actually use and deploy these type of new, I call responsible data use technologies. So that's what we developed, called the CoLearn, and the technology is called CoLink. But so the idea is we are building this decentralized data science platform where, for example, the work we did with Meta, it took many, many months to actually, from when we already, after designing the algorithm, had an initial prototype of implementation of the algorithm, and the rest just took many, many months to actually develop the production system. Whereas if we had the co-learn system back then, it could have shrunk this many, many months of engineering work into maybe just like 1 or 2 weeks.
Very cool.
So really the platform, the goal is actually integrates all these technologies that we developed, secure multiparser computation, and federated learning, and we are integrating certain differential privacy, the PrivateSQL technologies in there as well, so that
cool.
It's super easy for developers to use any of these technologies and also deploy applications in the real world.
Nice. So that sounds like a great take home for people here if they want to be incorporating the kinds of decentralized elements that you've described today to allow for a responsible data economy, then CoLink is the way to do that. And parts of it are available now.
And you can go to the website colearn.studio to learn more.
Colearn.studio, nice. So sitting in the front row here at ODSC West is Serge Massis, who is a researcher for the Super Data Science podcast. And so he did a lot of the research behind many of the great questions that I asked today. So thank you very much to Serge. But then I'd like to open it up. We have time for a couple of questions from the audience. So the context here is that there might be lots of industries out there that would be interested in these kinds of technologies beyond the examples that you provided today. Don, so asset management could be an industry that would really benefit from the kinds of decentralized intelligence technologies that you described today. And then there's a two-part question. So the first one is, do you think that companies adopting these technologies are doing it from an internal or an external motivation? And then the second thing is, what are the practical implications of using a querying tool like PrivateSQL? How do you, if you just use the star in your SQL query, in normal circumstances, you could be pulling out credit card numbers or social security numbers. So, how is practically the syntax different?
Mm-hmm. Okay. These are great questions. So first, I think right. I mean, for these companies, there are actually a number of reasons why now they are becoming more and more motivated using privacy technologies, both from external and internal concerns, absolutely, and also there is more regulatory requirements today as well. For example, GDPR, CCPA, and so on. So all these gives company more motivation now to deploy privacy technologies, which I'm really glad to see. I think the conversation today is very different from just 5 years ago or even just 2 years ago. So I think that's also why I really enjoy actually the conversation here. Is I think we do want to raise more awareness also for users and the society overall is to have more demands on your data privacy and give the feedback to companies that this is important and it's important for them to deploy and adopt more privacy technologies.
Nice.
So
and then the practical question.
Right. So that's number one, and number two. So it really depends on the queries. So in general, basically, the PrivateSQL results it will now return, for example, like a specific individual's records with their sensitive data and so on. So usually, for PrivateSQL, it's deployed on you can call it these statistical queries,
right,
or aggregate queries.
Right.
So in this case, will basically in the results that's returned. So basically, it will return you differentially private results. And also, you can, as I mentioned, so this query writer actually is very flexible. What we have done in the past is, of course, you can embed differential privacy mechanisms, but you can also embed other types of requirements. For example, in our collaboration with Uber previously, they have put in certain policy requirements, for example, certain columns that are sensitive. You simply just cannot even, write. You cannot do certain operations on that.
Nice. So Don, thank you so much for taking the time to be here, and let's give Professor Song a hand. Thank you.
Thank Thanks again for having me. Thank you.
What an incredible experience to be on stage with a luminary like Professor Song in front of the engaged live audience of ODSC West filming a Super Data Science episode for you. In today's episode, Don filled us in on how responsible decentralized intelligence allows the training of compute-intensive machine learning models that can be distributed across many machines without compromising on data privacy or security. She talked about how her responsible data economy collaboration with Meta AI enables Facebook and Instagram's algorithms to be more fair without sharing sensitive information from Meta employees. She talked about how homomorphic encryption, differential privacy, and multi-party computation can work together to facilitate the vibrant, responsible data economy of the future, how large language models like GPT-3 can memorize private data such as credit card numbers and social security numbers, and then reveal these private data to people who query the model, how PrivateSQL makes differential privacy easy to use, enabling a data analyst to access anonymous, aggregated data from a database that includes private information, and she left us with her resources for data scientists to learn how to make it easy to develop and deploy privacy-preserving machine learning applications. To get those, again, you can go to colearn.studio. All right, as always, you can get all the show notes, including the transcript for this episode, the video recording, any materials mentioned on the show, the URLs for Don's social media profiles, as well as my own social media profiles at superdatascience.com/633. That's superdatascience.com/633. Not just this episode number 633, but every single episode, I strive to create the best possible experience for you, and I'd love to hear how I'm doing at that. For a limited time, we have a survey up at superdatascience.com/survey, where you can provide me with your invaluable feedback on the show. Again, our quick survey is available at superdatascience.com/survey. Thanks to my colleagues at Nebula for supporting me while I create content like this Super Data Science episode for you. And thanks, of course, to Ivana, Mario, Natalie, Serge, Sylvia, Zara, and Kirill on the Super Data Science team for producing another trailblazing episode for us today. For enabling this super team to create this free podcast for you, we are deeply grateful to our sponsors. Please consider supporting the show by checking out our sponsors links, which you can find in the show notes. And if you yourself are interested in sponsoring an episode, you can get the details on how by making your way to johnkrohn.com/podcast. Last but not least, thanks to you for listening all the way to the end of the show. Until next time, my friend, keep on rocking it out there, and I'm looking forward to enjoying another round of the Super Data Science podcast with you very soon.